All right. So in terms of announcements, I sent out one yesterday. So Lachlan, the TA for this class, has STEM Center hours. Um, what I say, Monday and Wednesday from 5 to 7. So if you've got questions, if you're working to debug your projects, absolutely go visit the STEM Center and get some help on that. There's an event called Thank a Prof, which is the one that you guys can go to, or I guess you could go at 1 and then come here at 1:30 on Thursday. This is they're tabling outside of Oliver, and it's just a chance for you to go and write a thank you note to your professors of, I enjoyed your class. This is like, thanks for teaching it. Something like that. Professors always like to get those kind of notes. It's fun. Homework 5, make sure you justify why or what thing you implemented that goes beyond the requirements. Course evaluations. Let's maybe do that at the end. Because we'll finish the lab fairly quickly. So I'll give you the end of the class time to do the evaluations. Those evaluations, you will get many, many emails. They're really helpful for faculty to help improve the course of, they'll ask what went well, what didn't went well, what go well, what could improve your learning, what did you wish that you would do to improve your learning? And so questions like that. It's very reflective, so those are helpful. I'll give time for that at the end of class. All right, we're going to review the sorting algorithms, and then we'll do lab 9. Okay, so last time, way back when, not last Thursday, the previous Thursday, we talked about sorting algorithms. Here are ways that we can put things in order. And there are different ways to accomplish this. So we talked about 5 different ways. There are more than 5 sorting algorithms. There's a lot of them to varying levels of efficiency. Quicksort is generally regarded as one of the better ones. I think there's, what is it? TimSort is the best, last I checked. And it's kind of a play on Quicksort. MergeSort is also quite decent. Bubble, insertion, and selection are all, insertion and selection are decent. Bubble is not, but we'll discuss that. Okay, so if you want to pull up, there is the sorting algorithm cheat sheet. And if you want to pull that up for a second, I will also pull that up. All right, so we went through all of these last time. We talked, here's what the algorithm does. So remember, bubble sort, we go through the array, and as we could go, we compare each thing to the thing next to it until eventually we find the largest, and then we compare and swap, compare and swap, compare and swap, until the largest thing bubbles up to the end. And so if we look at our cheat sheet, I think this first one would be bubble sort. So just eyeballing it, what do we think the big O of this is? Hearing n squared? Right. So we've got a loop that goes to n minus 1, basically n. We've got a loop that goes 1 to n, basically n. And so we do the thing in the inner loop n times, and we do, so there's n times n, that gives us O of n squared. So bubble sort is O of n squared. All right. Next is insertion sort, where we're keeping track of what part of the array is sorted so far. And we work left to right, and we take each new thing, and doesn't matter if it's the smallest or the largest, we swap it until it's in the place where it should be in our sorted part of the array. And so we work left to right until all of the array is our sorted part of the array. So is it this one? No, because insertion sort doesn't have anything to do with a minimum. What about this one? Yeah, I think it's this one. So the way I can tell is, well, we've got a for loop that goes from the beginning to the end. And then we have a while loop that I'm not quite sure where it starts. It starts wherever I is, but it goes until I gets to 0, and then it does swapping. So eyeballing it, what's the big O of this one? Turn to your neighbor. Hazard a guess.
Oh, wow. Like it's not just.
If it's not just n squared, why?
That's a good question.
All right. What are your thoughts? Start with N. Do you say M? N for the for loop? Okay. Okay. All right. Other ideas?
Is it N log N?
N log N. Why would it be N log N? What about the while loop makes it log N? See, that's the thing. So like for log N, there has to be some sort of like repeated division or repeated multiplication. Is that happening here? I would argue no. Summation, okay. Other guesses? So why is it not just N squared?
Because the while loop isn't iterating through and it's going through the indexes.
Okay, so let's think about the indexes then. So what is the best case scenario for the while loop? J equals 0. Yeah, maybe. But since I is going from 1 to n minus 1, then that wouldn't happen. But if you think about it, so the while loop, so what this while loop is doing is we say that first off, here's the cutoff for our sorted part of the list. and then we take the next thing. And while we haven't reached the end of our list, and while this thing is not in the correct spot, we swap it. And so we keep swapping. That's the while loop. That's the while loop's job. The best case is that we don't have to do any swapping. The best case is that that is false, right? The best case is that these two things are in the correct order. So if that's the case, then we just wouldn't do the while loop. This is why insertion sort is the fastest if the array is already sorted, because if it's the best case, it's just O of n, where we just start at the beginning, loop all the way through to check, we're done. In the worst case, though, let's think about the worst case. If everything, let's say everything is reversed, then for every new element, we're going to have to swap it all the way to the end of our sorted partition. Every new element, we swap, 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 swap. And so in the worst case, with n elements, we're going to have to do n swaps at the very end. And so that's why in the best case, it's O of n, which we can also call order n. But in the worst case, so for example, think like it's completely reversed and we just need to swap everything around. In the worst case, it's n squared, which you'll notice is the same as bubble sort. All right. So for selection sort, we're similarly building our sorted part of the array. This time we scan through, look for the smallest thing, and then we build up that sorted part by taking that smallest thing, swapping it with whatever would be here, and sticking it there. Go through, find the smallest thing, put it right next to that. Go through, find the smallest thing, put it right next to that. That's selection sort. What's the big O of this algorithm? Yeah. N squared as well. Yeah. We've got a for loop there, 0 to n, basically. This from j plus 1 to n. So it ends up being like a summation again. But in the worst case, if we were to write all that out, we would get something n times n minus or plus whatever. But that just gives us n squared. And so selection sort, worst case, is also n squared. All right. Merge sort. So merge sort is we take the list, we split it in half, and then for each half, we split it in half again until we get to single elements. And then we go through our single elements and we merge them into a new list. And we merge them so that they're in order. So like we split 3, 1, 5 into 3 and 1, 5, which we split into 1 and 5. And then we merge 1 and 5 back into a single list. Then we merge 3, 1, and 5 back into a single list. And in that way, the merging is doing the actual sorting. So we do that on each side until we come with our finished list. Merge sort is where we start to think not only about time complexity, so the amount of steps that an algorithm takes, but we also think about space complexity. Because if you think about it, even when we're drawing it out, if we're looking at selection sort, we can do all of this what we call in place. where we don't need to, if we're sorting a bookshelf, we don't need to like pull books out and stick them into piles and spread them all out over the carpet. We can just do this in place on our bookshelf. With merge sort though, it's not in place. It can be done in place and complicated, but it can also be done not in place. And so then we have to think about space complexity as well, of how much space, additional space do we need to get this done? And so for merge sort, our space complexity is at worst case n, because we have n books on our bookshelf. So we'll need to take all of those out. So we need to have at least that much space to do our job. But for time complexity, let's look at the algorithm. I think that's quicksort. All right, okay, it's not going to fit on one page. Anybody want to hazard a guess for merge sort? Talk to your neighbor. Do you think it's less than n squared or equal to n squared? All right, what are we thinking? Heard things about a log. Are we repeatedly dividing? Are we repeatedly dividing? Yeah, I would say so, because we take the list, split it in half. Take that remaining list, split it in half. We're repeatedly dividing it by 2. So there is a log n component to this. So there is a log n. Is that it? No. Why? Well, yeah, so if we think about it, like the merging is where the sorting actually happens. And in doing so, we have to go through each of these lists. And so by the time we've gone through all of the lists, how many elements will we have gone through? N, because that's all of our elements. So yeah, so merge sort ends up being worst case of n log n time, which is better than n squared. All right. Anyone want to hazard a guess at quicksort? Remember, quicksort is where we choose some element, usually either the first, the middle, or the last, and we say this is going to be our pivot element, where we're going to then partition the rest of the things. So we're going to look at each thing, compare it to the pivot element, and then put it in one of 2 piles. So either it goes before the pivot element, or it goes after the pivot element. And then we do quicksort on each half and repeat. Are we doing repeated division? I think I would say so. Let's look at, so this is quick sort. I think this is, yeah. So, right. So if we think about it, the partitioning is where the sorting is actually happening. And so whenever we partition, we are dividing the list into two and then running quicksort on each side. So there's the log n part. And then, but when we partition, we're checking each element against the pivot. And so we check, at the worst case, we're going to check n elements at the very beginning. And so for that reason, because we're doing this division and we're in the partition, we check each thing against the pivot element. This also is n log n. But again, so this is generally, we talk about worst case when we think of that, like the list is completely reversed. And generally it's not that bad. And so we have to think about worst case as computer scientists. Generally it's somewhere in the middle. And so if you go on to take analysis of algorithms, you'll learn about other categories of ways we can classify an algorithm. So we've talked about big O, which is worst case. In 374, we'll look at big omega, which is best case. And so we think about that with insertion sort of that's the best case scenario when the list is already sorted. We also talk about big theta, which is average case, which depends on what the worst case and the best case is. All right. So I think, let me go back to my notes. I think that's good to go. I'm going to pause the recording. I'll put you in groups for lab 9. And the plan is for lab 9, I would like you to each create a Google Doc and then share or create a shareable link and give editor access to that link. And then you can share that with your partners and submit it to Canvas. So I'm trying just a Google Doc for this one. I'll put you in groups, I'll put the groups in Canvas, and then we're good to go. And I'll give you probably an hour, and then the last 10 minutes of class we can reserve for evaluations. Sounds good? Cool.